Hi everyone. Today I will talk about object detection and recognition for autonomous vehicles. Object detection and recognition is a field of computer vision that focuses on identifying and recognizing objects from images and videos. It has several applications such as farming and agriculture, traffic monitoring, and surveillance and security systems. This project will focus on autonomous vehicles. Autonomous vehicles are equipped with sensors such as cameras, LiDAR, and radars to enable autonomous navigation and decision making. Object detection generally consists of two tasks: localization, which involves locating an object in an image, and classification, which requires assigning a class label to that detected object. Typically, algorithms fall into two categories: one-stage and two-stage detectors. YOLO and MobileNet are examples of a single-stage detector, and RCNN is a two-stage detector. This project focuses on training and evaluating the YOLO algorithm for object detection and recognition on a dataset incorporating a range of illumination conditions and viewing angles. Two safety-critical capabilities that are emphasized in this study include multi-class recognition, which ensures different types of road users are correctly identified, and localization accuracy, which measures how precisely bounding boxes align with the detected objects. Going back to multi-class recognition, each vehicle class has its own safety implications, which is why they all require equal representation in the dataset. Motorcycles, bikes, and pedestrians are more vulnerable and hence require higher recall to avoid catastrophic consequences. Larger vehicles require high precision to enable safe maneuvering of vehicles. The overall goal here is to assess YOLO's performance in recognition and localization for safe autonomous vehicle navigation. YOLO is generally preferred for object detection and recognition in autonomous vehicles because it performs detection in a single evaluation, enabling high-speed real-time performance while maintaining strong accuracy across multiple object classes. YOLO version 8 was used due to its superior performance across multiple vehicle classes compared to earlier versions. Three different losses are used by the model to evaluate performance, and this includes box loss, classification loss, and distributional focal loss. A CARS detection dataset from Kaggle was used in this study. The dataset contains a total of 1,254 images across 5 different vehicle classes. The figure on the right shows a clear class imbalance in the dataset, with cars having the maximum number of training images and the other classes being underrepresented. Model training was completed in Colab. The optimization process began by fine-tuning a pre-trained model on the chosen vehicle detection dataset. The fine-tuning strategy used here involved freezing all the layers except the spatial pooling pyramid modules, as it was found to be far more effective than freezing the whole model except for the detection head. Data augmentation is automatically applied by YOLO, and the default parameters were retained as it was found to be far more effective than using custom values. Hyperparameter fine-tuning was also conducted to achieve optimal results, and the final values of these parameters that was used during model training is shown in the table on the right. The metrics used to evaluate model performance include precision, recall, mean average precision, and IOU. IOU, also known as intersection over union, is a measure of localization accuracy. The figure on the left plots the training and validation curves for the model, which includes the box and class loss. It can be seen that as the epochs increase, the training and validation loss both decrease. The validation loss curves indicate the model's improvement during training. Initially, the validation class loss is high, but it drops steeply after 5 epochs, indicating rapid learning capability of the model. Thereafter, the training loss curves gradually decrease while validation curves stabilize. The figure on the right plots the mean average precision of the data. Both curves show a steep initial rise, indicating rapid learning of the object detection features. Over time, the curves plateau, reflecting convergence of the models. MAP50 stabilizes at a higher value due to its more lenient IOU threshold, while MAP50 to 95 stabilizes at lower values, as it has a stricter requirement for accurate localization across multiple thresholds. These figures show results of object detection and recognition on a sample of the test images. Each image includes a bounding box, a classification label for the vehicle, and a confidence score for the classification label and bounding box. It can be seen that the model is able to accurately recognize all classes of vehicles in the images with a confidence score greater than 80% under a variety of lighting conditions and viewing angles. The model is also able to detect and recognize more than one vehicle in the image, regardless of whether they belong to the same class or not. This table provides a summary of the model's accuracy in recognizing different vehicle classes both individually and overall. It can be seen that the multi-class recognition system performs well, with an overall precision of 80% and recall of approximately 82%. Hence, the model is able to distinguish between different vehicle types. Results also show that vehicles such as ambulances and buses have near perfect results, whereas recall is lower for cars and motorcycles. It is likely that cars are often missed when several of them appear in the same image, causing recognition errors. This is what the two figures at the bottom of the slide are indicating. IOU is used to measure localization accuracy, which quantifies the overlap between the predicted bounding box and the true bounding box. Values close to 1 indicate strong alignment between the two boxes. This table summarizes the IOU scores for different vehicle classes. It can be seen that ambulances have a near-perfect localization accuracy. Cars, buses, and trucks have lower IOUs, but still show strong localization performance. The lowest IOU is for a motorcycle. This could potentially be due to the complex shapes or occlusions in the dataset. There are a number of lessons I learned from this project, which I will quickly go through. Firstly, a diverse dataset proved essential for training a robust detection model. Autonomous vehicles encounter objects under varying viewing angles, occlusions, and lighting conditions. Without sufficient diversity, the model is at risk of failing in real-world deployment. Secondly, the dataset exhibited clear imbalance, with cars being heavily represented, while other vehicle classes were underrepresented. It was interesting to note that precision and recall were not highest for cars, even though cars had the largest number of images in the dataset. This highlights quantity of images is not the only factor contributing to superior performance. YOLO's data augmentation alleviated some of the effects of class imbalance, but a balanced dataset is required to achieve consistent performance across all classes. Thirdly, YOLO's default data augmentation parameters were found to be more effective than using custom values. This suggests that YOLO's default augmentation parameters are well optimized for object detection tasks. And finally, localization accuracy varied across vehicle types. Larger vehicles such as buses and trucks were easier to localize, while smaller vehicles such as motorcycles posed greater localization challenges. This highlights the need to improve localization of smaller objects such as motorcycles and bicycles, which is critical to the safety of autonomous vehicles. This project trained and evaluated the YOLO model for object detection and recognition on an autonomous vehicles using a car's detection dataset. The algorithm's performance on multi-class recognition and localization accuracy was successfully evaluated. With overall precision and recall exceeding 80%, the model performed well and was able to recognize all classes of vehicles. However, per-class metrics revealed that certain classes, such as cars and motorcycles, had lower recall. This was likely due to crowded image scenes that made detection more challenging. In terms of localization accuracy, larger vehicles exhibited better performance, with motorcycles having the lowest IOU. The main takeaway point here is that dataset balance is critical, as we need more training images for underrepresented classes, and YOLO version 8 shows strong potential for autonomous vehicle safety, but dataset diversity remains key. Based on these results, the following recommendations are made for future work. Current results indicate lower accuracy for smaller vehicles such as cars and motorcycles. It would be valuable to compare performance on the same dataset with the two-stage detectors such as RCNN. Two-stage detectors often achieve higher accuracy on smaller objects even if they are slower. YOLO's default augmentation parameters proved to be better than using custom values. Future work could apply augmentation techniques specifically to smaller objects or underrepresented classes. And finally, YOLO's augmentation techniques helped mitigate effects of class imbalance, but future work could use augmentation techniques specifically targeted at underrepresented classes. These techniques include oversampling and synthetic data generation.